So yesterday we left off talking about how banked curves work. Okay, we bank a curve in order to get added centripetal force to help us stay in a corner. All right, so having a bank curve can do a couple of things. A bank curve can guarantee, and this is the number one reason to have it, can guarantee a safe speed regardless of the road conditions. Okay, if I bank it at a certain angle for a certain radius, there is a speed that I could take that corner at that I would traverse it safely, even if it was covered in a completely frictionless material. Not that anything like that exists, but if it did, I would be able to still negotiate that corner safely as long as I took it at the design speed. Right? In real life, obviously a bank curve has friction as well as the angle of bank to help keep us in it, which means that it gives us added centripetal force, allows us to take the corner more at a higher rate of speed, essentially. Okay, which is why, of course, NASCAR tracks are banked. Okay, I'm not saying that you should take exit ramps or on ramps faster than the recommended speed. I would never do that. Okay, I would never recommend that you do that. So I'm not saying that. I have it on record now. Okay, but obviously, if there's friction as well as that force, then if it says the recommended speed is 40, then obviously if there is friction, you could traverse it at a faster rate of speed. Not a lot faster, because as we learned, centripetal force is exponentially related to speed. So the more I increase my speed, the more centripetal force exponentially would be required to keep me in the curve. So it doesn't take long before beyond that recommended speed, you are risking like sliding out or skidding out. Okay, so we talked about this diagram, okay, and we had kind of drawn on here that we have the normal force. Okay, and that normal force is not just due to the car sitting on the road, it's also due to the fact that the car is going around the corner and thus pushing on the road as well. So the normal force is larger than gravity. Okay, so gravity becomes this side of the triangle. Okay, so we have, whoa, every morning. Okay, so those two sides are related by how steeply the corner is banked. Right? If this bank gets bigger, so this angle here gets bigger, then the centripetal force will increase. Okay, normal force will come out here, and my force of gravity doesn't change, right? But my centripetal force would get bigger as a result of the increased bank. Everyone all right with that? Okay, but that also means you have to go faster in order to stay in that corner, because the more you bank it, okay, the more likely you are, if there's not a lot of friction, to slide into the middle if you're not traveling at the recommended speed. Okay, so we have this relationship here. This is the opposite side of that triangle. This is the adjacent side to that triangle. Everybody with me there? How do I relate the angle between the opposite and adjacent sides? Tan. Okay, the relationship between opposite and adjacent sides is tan. So really what we're saying here is that the tan of theta equals FC divided by FG. Okay, and if we fill in the formulas, we'll derive the formula used to design banked curves. Okay, so if I plug in mv squared over r, okay, and then I'm dividing that by the force of gravity. So essentially that just goes down here. Okay, so I've got mv squared over r divided by r times m times g. I've got an m on the top and the bottom. What happens to it? It cancels. Okay, so our formula then ends up as the tan of theta, or the angle of bank, okay, is going to be v squared divided by r times g. Okay, that is the formula used to calculate either the speed that the curve can be negotiated at, if I know the angle and the radius, or the angle it needs to be banked at if I know the radius and the speed. Okay, so that's how those things are related. You will never be asked to derive this formula. Okay, it will be on your formula sheet. In fact, I think it is already. Okay, but it's definitely on the one on the unit exam. But that's the bank curve formula. Okay, so whenever we're dealing with a bank curve, that's the formula we're going to use. You won't have to derive it, but that's how it is derived. So the faster I want to go, the bigger the angle needs to be. Agreed? That's what this formula would say. Bigger the radius, the smaller the angle needs to be. Okay, as long as we understand that. All right, so this is just showing what we just did here, okay? So we got opposite over adjacent, okay? That's just the derivation there. All right, so that indicates that for a given speed, v, the centripetal force needed for a turn of whatever radius, okay, can be obtained from the normal force by banking the curve at an angle, right? And that's all this is showing here. Right? It's also showing that, of course, we would have a force of static friction because this is an inclined plane. In the real world, where it wouldn't be perfectly frictionless, we would have a force of friction. But that force of friction doesn't act entirely into the center. It acts down the plane. Okay? That's what keeps us from sliding out of the plane. All right? It does have, of course, a horizontal component that's directed back in as well. We never deal with bank curves that have friction. We always deal with bank curves that are frictionless. Okay? It does add in quite a bit of extra calculation. Not that it's hard, but it's just a lot of extra calculation. All right, so example here. If I want to determine the angle at which a frictionless curve should be banked for a speed of 35 meters per second and a radius of 550, okay, what would that angle have to be? All right, so we would have our bank curve formula here, tan of theta equals v squared divided by r times g, and then we would plug in our numbers. 35 meters per second, all squared, divided by, and then this would also have to be in squared brackets, 550 times 9.81, so our radius times gravity. Right? When we do that, we get that the tan of the angle is 0.23. Right? If we want theta, then we have to go inverse tan of that value, and we get that it would have to be banked at 13 degrees. Okay? I know that doesn't seem like very much, but most banked curves that the average Joe population would use are not banked much more than that. Okay? Many of them are actually around that number, between like 10 and 15. You bank them any more than that, and they just become crazy. Okay, like they look like a NASCAR corner, and they're hard to pave, they're hard to keep clean. Okay, all of that kind of stuff. So we don't want to have them too banked. Okay, any questions on how that one worked? All right. So have you guys do a couple of example problems, not that one. Okay, just to review a couple of things here. These are not to do with curves, like with bank curves or anything, but just to review a couple of things here. Okay, this has to do with t equals 1 over f. We talked about that the first day. F equals 1 over t. Okay, remember that period is the time for one cycle. Okay, and that means that it is in seconds. Okay, the units are in seconds or minutes or years or whatever. Okay, but it would probably be seconds per cycle, whereas frequency is the number of cycles per second. Okay, and cycles per second are abbreviated hertz. Okay, Hz. Right, so if you have like a equalizer or something like that for your stereo, you can select what frequencies of sound get amplified. Okay, like if you have an amplifier for a subwoofer, okay, there's usually a crossover switch in there where you can tell it you want to amplify everything below 60 hertz, which means your car sounds like thunder. Okay, you can amplify everything below 150 hertz, which means it sounds like thunder, but there's a little bit more clarity to it. And then like anything below 250 hertz is not really rumbling anymore. Okay. Everybody kind of follow there? Okay, so hertz measures the frequency, how many times something oscillates. With a subwoofer, if you have it oscillating or only amplifying under 60 hertz, you can watch it move. Okay, if it's like really, really loud, you can watch the speaker cone go back and forth. Okay, anyone ever seen that? Yeah, watch the sub go back and forth. Yeah. Okay. I was once young and silly too. It was just a long time ago. All right. So if I have a propeller of a toy airplane rotating at 300 revolutions per minute, what's its frequency in hertz? Well, that means I want it in revolutions per second. So I take this number and divide by 60. Okay, so nothing hard there. Okay, if I have an electric motor that rotates at a frequency of 40 hertz, what's its rotational frequency in RPMs? Well, then I would not divide by 60, but multiply by 60. Okay, and a medical centrifuge, that's the one you sometimes see in like the crime scene shows. Okay, they put the little vials in there and it spins them around and around. That's a centrifuge. Okay, separates blood into parts. It can spin at 6.0 times 10 to the 4 RPMs. Okay, what's its frequency in hertz and what's its period? So in hertz, we would take this number and divide by 60. Okay, so we would have 60,000 because that's what we're looking at there. Okay, so it's 1,000 hertz. That's fast. Okay, that's 1,000 times per second. Really fast. Okay, if I want to find out its rotational period, I go 1 over that number, right? Because T is 1 over F. Whoa. Okay. So I go 1 divided by 1,000. Whoa. All right, so 1 revolution of the centrifuge takes 1/1000th of a second. So that thing's spinning pretty darn fast. Okay. All right. We talked about this example a little bit the other day as well. If I had a pebble that was stuck in the treads of a tire and it was 36 centimeters from the axle, so they give me the radius, okay, it takes 0.4 seconds for the wheel to make 1 complete revolution. What's the speed of the pebble at any one instance? So they gave me R, 0.36 meters, okay, and they gave me the period, 0.40 seconds. Can I find speed with that information? Okay. First day we went over a formula that would help us calculate speed, and it was, except that this is a circle, so the distance is the circumference of the circle, okay, which means that this formula became this, 2 pi times r over t. Okay, do I have that information? Okay, so v equals 2 times pi times 0.36 divided by 0.4. All right, so it's moving at 5.6, 5.7 meters per second at any one time. Okay. All right, so these are all the kind of basic calculations that we're going to need to be able to do in this unit. All right, I'm going to let you guys try those two. Okay, keeping in mind that they're trying to trick you with units here. Okay, they're giving you kilometers and kilometers per hour. You're going to need that in meters per second if you're going to be able to do anything with it. Meters if you're going to do anything with that. Okay, so we're looking for how much time it takes for the tires of the race car to make 1 revolution. In other words, we're looking for period. Okay, that's the time for 1 revolution. The car is traveling at 261 kilometers per hour. Okay, so I know V, it's 261, but if that's in kilometers per hour, I need that in meters per second, so I need to divide that by 3.6. Okay, so 72.5 meters per second. All right, so now I have V, okay, and I also know the radius is 0.350 meters. All right, with those two things, I should be able to calculate T using V equals 2 times pi times R over T. Right, that's the formula I would have to use here. I need to solve for T, so I'm going to multiply both sides by T, okay, and then divide both sides by V, and that'll be my formula there. So that'll be 2 times pi times 0.35 divided by 72.5. All right, so we're getting 3.03 times 10 to the minus 2. Yep. Okay, and how many significant figures does that answer have? 3. Okay, the leading 0 isn't significant. I think a few people still are making that mistake, okay, because I saw it a few times on the unit exam on question 1. Okay, the leading 0 is not significant. Okay, keep that in mind. All right, how many people need some more time on number 2? Okay, I'll give you a little bit more time on 2 then. All right, let's have a look at number 2 here. So, in 2006, an Alberta astronomer discovered the fastest spinning collapsed star, okay, which is known as a pulsar. Okay, it's called a pulsar because actually in an X-ray telescope it pulses. Okay, so it was the fastest spinning one ever found. It only has a radius of 16.1 kilometers, which is 16,100 meters. Okay, and is spinning at a rate of 716 hertz. That means it spins around entirely 716 times in 1 second. Okay, now remember, this is a collapsed star. It's also incredibly massive. Okay, and it spins around really, really fast. They're one of the freakish things that's out there in the universe. Okay, so we know the frequency then is 716 hertz. What is the speed of it at its equator? All right, so we've got V equals 2 times pi times r divided by t, but we don't have t. So we could do this in 2 steps by going 1 over f and finding t, or we could just understand that really this is also 2 pi r times f. Okay, so when I plug in my numbers here, it's just going to be 2 times pi times 16,100 times 716. Obviously, this is going to be a pretty big number. All right, so it's traveling at 7.24 times 10 to the 7. Whoop, add one more to that. So 20 million. Yeah. Yeah. Fast. Yeah. Yeah. All right, to give you some idea, just as a comparison, the speed of light is 3.00 times 10 to the 8 meters per second. So these things are spinning really fast, really, really fast. If you were near it, I don't know if you would or not. I think the pulsing is more a Doppler effect thing, where part of it is coming kind of towards us really fast, and part of it's going away really fast, which tends to give it a change in frequency kind of a thing. But I don't know. If there were features on its surface, maybe, but it'd be spinning awfully fast. It might not be hard. It might not be possible to actually see it spinning at 716 hertz, right? Like a really good high-speed camera can take, 240 frames per second, which means it would only catch it rotating 1 out of every 3 times. So yeah, it'd be hard to see. All right, so that one we don't need to go over. Okay, but this we can look at. We talked about centripetal acceleration the other day. Okay, AC is v squared over r. Okay, so a couple of these questions have to do with centripetal acceleration. So I'll have you guys give those a try and see how we do. I will make that a little bit bigger. Okay, so on number 3, we have a helicopter blade whose diameter is 14 meters. What does the formula need? Radius. Okay, so the radius is 7 meters. Okay, once in a while a question will do that just to see if you're paying attention. Okay, the centripetal acceleration is 2,527. So meters per second squared. Okay, what is the period of the helicopter blade? All right, so we have this formula. It doesn't have period in it. But if I have velocity, could I find period? Okay, or I could even do this in 1 step. All right, I could change this formula by substituting. And substituting is something we'll have to do a fair amount in this unit. Okay, what I mean by substituting is I know the formula for V is 2 pi r over t. Can I substitute that in for V? And then I don't have to solve for V and then manipulate V's formula and solve for it. Okay. The only issue is that V is squared here. So what do I have to do with its formula? I have to square everything. So V squared would be 4 pi squared times r squared over t squared, and then there's also still that r from before that would be in there. Okay, so I've just substituted in V's formula so that I don't have to do two things. Okay, now there's an r on the top an r squared on the top and an r on the bottom, so they're going to do a little canceling, like so. Can I solve for t now? Since that's what the question asked for. So I'm going to bring t over to this side, actually t squared over to this side, and then I'm going to divide both sides by the centripetal acceleration. Okay, and I've got my formula for t squared. That would be my formula for t. So t will be the square root of 4 pi squared times r over ac, which is going to be, I don't know why I wrote that again, 4 times pi times 7, sorry, pi squared times 7, divided by 2,527. Okay, so we're looking at 0.33 seconds, okay, which is what they've got there. All right, and if you wanted to do that in 2 steps, you could, but there are going to be points in this unit where you're going to have to substitute because there'll be no way to do it in 2 steps. Okay, so just so you know, being able to substitute another formula into an existing formula is an important skill. Questions on any of those? Okay, can do 2? Yeah. All right, so we have, so a top, I don't know if you guys, like, you spin it and it just spins around and around. It's kind of a cone shape. Okay, so it has a centripetal acceleration of 125 meters per second squared at the edge, which is 0.03 meters, 3 centimeters from the axis. What's the speed of at the edge of the top? So we got V equals, again, A equals V squared over R. Right, so we know what t is. We know what r is. Okay, we're looking for its speed of rotation. So all we're doing is going to multiply both sides by r and then square root that, and we'll have v. Okay, the key is that we have to convert r to meters. So 0.03 meters times then our 125, okay, and then square rooted that should give us 1.94. All right. Okay, so for this example here, this is a FC question, so a centripetal force question, but a very basic one. We want to determine the magnitude of the centripetal force exerted by the rim of a dragster's wheel on a 45 kilogram tire. Okay, so when your tire spins around and around, okay, the tire wants to come off. Okay, if it wasn't for the fact that there was air pressure pushing the tire against the rim and holding it there, along with the little bit of adhesive they put on there, okay, the tire would come off. Okay, I mean, it's spinning around and around in a circle. Okay, it's going to want to peel away, and sometimes that happens on drag racers and things like that. Or if the tire goes flat and you drive on it for too long, you'll peel it away. Okay, or it's low for too long, you'll eventually peel the bead away and the tire will come off. And you don't want that. You shouldn't drive on your tires if they're low. Okay, in case you didn't know that. Of course, if you depend on your tire pressure sensors to tell you when they're low, they're always low because tire pressure sensors inevitably just fail, okay, on most things, and they're always telling you it's low. All right, for this one, we have a radius of 0.480 meters. We know the speed is 30 meters per second, okay? FC is mv squared over r, okay? They told us the mass here is 45 kilograms, so we don't even have to manipulate. It's just going to be 45 kilograms times 30 squared divided by 0.480. Okay, is that a lot of force? 84,375 newtons. It is a lot of force, okay? But it takes a lot of force to hold your tire on, especially if you're a drag racer and you're spinning it around, and it's, they often run those only partially inflated. Okay, it's actually pretty cool. If you watch them in slow motion, you can actually see the tire like fold a little bit as it starts to spin. Okay, so try these ones. They're pretty basic. They're basically like what we just did. So give them a bit of a try there, see how we do on those ones. So we've got this pebble that's stuck in the treads of a dirt bike's wheel. Okay, the radius of the wheel is 23 centimeters. Again, we need that in meters. Okay, so we have mass 0.0021, so it's pretty small. Okay, the radius is 0.23 meters, and we have a centripetal force of 0.66 newtons. We're looking for V. All right, so FC equals mv squared over r. So we're looking for v, so we'll multiply both sides by r, divide both sides by m, and then square root to get v. So we'll have 0.23 times 0.66 divided by 0.0021. All right, so we're looking at 8.5 meters per second. All right, questions on either of those? All right, so we haven't done any of the ones like what we did yesterday where we had, okay, FC is equal to this force, it's equal to friction, or it's equal to gravity, or whatever. Okay, that's what we're going to be getting into next, is figure out what the centripetal force is and set those two formulas equal to each other. Okay, so this is like what we talked about yesterday with an unbanked curve. Okay, what holds you in an unbanked curve is the force of friction. So when we're reading through this problem here, we're trying to find the maximum speed, so we're looking for V, okay, at which a 1,500 kilogram car, okay, can round a curve with a radius of 40 meters with a coefficient of static friction of 0.6. Okay, that's the information we have. Well, we know that the centripetal force in a banked curve is, or sorry, an unbanked curve is provided by the force of friction. Because it is unbanked, we also know, okay, that when we set up this formula and we say that Fc is mv squared over r, that the force of friction is mu times the normal force. But since it's flat, normal force is equal to gravity, right? So we got m times g. So if we're looking for v, that means we got to multiply both sides by r. We've got to divide both sides by m, which is going to make m just cancel because it's on both sides. And then we got a square root. Okay, and this is what we got the other day. V is the square root of mu. Okay, so v equals the square root of 0.6. Okay, that's our coefficient of friction, times 9.81, our acceleration due to gravity, times 40 meters. Right? So we didn't even need the mass. They didn't even have to give it to us in this question. Okay, so V is going to be then the square root of 0.6 times 9.81 times, sorry, it's 40 meters, not 400 meters, 40 meters. All right, so the speed is going to be 15.3 meters per second. Okay. Everybody all right with how that one works? That's going to be a lot of this unit, figuring out what the centripetal force is, setting the formulas equal, okay, or having to do a net force calculation where Fc is the net force and it's this force and this force. Okay, very similar to what we did before. Okay, so I'm going to blow these ones up so they're a little bit bigger. Okay, so give 1 and 2 a try for right now. Okay, so the skid pad test is how I talked about that the other day. It's how they test how well something can corner, right? So they go around and around in this circle that has a radius of 100 meters. Okay, at ever increasing speeds, the prototype car is 1,200 kilograms. Okay, and we're looking for the coefficient of friction if it takes it at 95 kilometers per hour. I don't want that in kilometers per hour. I want it in meters per second. Okay, so 26.388. All right, so I have those things, and I know that in an unbanked corner, centripetal force is provided by friction. So we have mv squared over r equals mu times the normal force, which is equal to gravity because it's unbanked. All right, so I'm trying to find mu this time. So I'm going to divide both sides by mg. Right off, I know that the m's are going to cancel, and g is just going to end up over here. All right, does this look anything like another formula we talked about? V squared over rg. Okay, corners have stuff in common, right? I'm solving for the thing that influences the corner, friction, okay? I'm solving for the thing that influences the corner, bank. They have the same three things affecting them: the speed, the radius, and gravity, right? So it's only natural that their formulas should be similar. Okay, so we have mu here, okay? And so we're going to have 26.38 repeating squared over our radius, which was 100 meters, times gravity, or sorry, times, yeah, gravity 9.81. So we didn't even need the mass, but they always give it to us anyway. Okay, so we got a coefficient of friction of 0.710 for that one. Okay. All right, and then for number 3, you haven't done one where you solve for radius yet, so give that one a try. See how we do there.